talk about where we left from. We are going to talk about the ideal gas law. There is a little problem that I have put up on the screen, and I put it up a bit earlier, so those of you who came in could have seen it. Hopefully you already solved it, just to give you a flavor of how to use the perfect gas law. This is something you have almost certainly seen in your freshman chem or even before that, but let's work through this. After that, what we are going to do today is to talk about mixture of gases, and then we will look at the kinetic model of gases, try to get a bit more quantitative perspective into the things that we have mentioned about pressure and temperature. We will then talk about a little bit about real gases, and then beginning next week, we are really going to get to the heart of the matter, which is first law of thermodynamics. So beginning Monday we don't have a class, it's Labor Day. Beginning next Wednesday, you should have a working knowledge of multivariable calculus. You should be able to tell the difference between total derivatives and partial derivatives and things like that. So there is already online material about the modules, and I will also have the exercises up by Monday. Okay, any questions about the material so far? It's been really easy so far, right? That's the feedback I have gotten from some of the students, but don't worry, it will get hard before you know it. It ramps up gradually. It's like going on a hike where it's very, very pleasant, and before you know it, you're really like scrambling up. And you'll get that feeling. So don't get too casual. Okay, let's work through this problem. It says, in an industrial process, nitrogen gas is introduced into a vessel of constant volume at a pressure of 100 atmosphere and a temperature of 300 Kelvin. The gas is then heated to 500 Kelvin. What pressure would the gas then exert, assuming that it behaved as a perfect gas? So in problems like this, don't worry about whether to use Charles' law or Boyle's law or whatever it is called. Just remember the ideal gas equation. So this problem is straight from Atkins. I don't know what's the number. I will just write down as the Atkins problem. And we will start with PV is equal to nRT. That's something we know. And we are going from some temperature 1 to some temperature 2. We are going from one set of variables. Remember, these are all variables of state. We are going from one set of variables of state to another set of variables of state. So that's going to be, that implies that P1V1 by N1T1 must be equal to P2V2 by N2T2, right? In this case, in addition, we know that a chemical reaction has not happened, so the N has not changed. So N1 is equal to N2. Furthermore, we have been given the information. So this is example 1.A.1. It's like the very first example in Atkins. It's also said that the vessel is at constant volume. So V1 is equal to V2. So when we plug these two things in, we get P1 by T1 is equal to P2 by T2. Therefore, P2 is equal to T2 by T1 into P1. And that gives us 500 Kelvin divided by 300 Kelvin into 100 atmosphere is equal to 167 atmosphere. It's a simple problem. For those of you who are going to take GRE or MCAT or things like this, they tend to have a lot of problems like this. It's just that there's so many of them that you can often end up making mistakes. So that's a simple use of the equation of state. It's not just equation, it can be quite practical. Of course, for most systems, this ideal gas approximation will not be applicable. We will be looking at complications to that, and we will be looking at some more realistic equations of state shortly, probably today or on Wednesday for sure. So that was a practice problem. If there are some more students join. So any questions about ideal gas law so far? You can just unmute yourself and ask, or you can ask on Slack, or you can ask on Zoom chat, whatever you want. Okay, it's no question, which is not surprising. It's quite, yeah. So let's look at mixture of gases. What can we say that if in our vessel that we have been considering so far, we have N1 moles of gas 1 and 2 moles of gas 2, and so on and so forth. We have a bunch of other gases. So we can define mole fractions. Mole fraction x1 will be n1 by n, where n is equal to n1 plus n2 plus howsoever many gases we have, right? So this is the mole fraction. You can define it for x2, for x3, and things like that. So this way, we will define the partial pressure as for gas J, it will be different for every gas. The partial pressure for gas J will be called Pj, and it will be given by Xj multiplied by the total pressure of the vessel. This is a definition. This is always going to be true. This is true. So far, see, we haven't used any ideal gas law or anything like that. The gas could have been highly interacting. All molecules of gas 1 could be bumping against each other, talking to each other. They could be talking to molecules of gas 2 and vice versa. It could be highly complicated. So this is true for all gases, perfect or real. Well, it doesn't matter. It's true for all gases. And you can see what this means per construction is, so we had Pj is equal to Xj times P, right? So this means that P is going to be P1 plus P2 plus P3 plus dot dot dot. Why? You can see why this is true, because P1 is equal to X1 times P, P2 is equal to X2 times P plus X3 times P plus dot dot dot. So that is X1 plus X2 plus X3 plus dot 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 multiplied by P. And what is X1 plus X2 plus X3? That is N1 by N plus N2 by N plus N3 by N plus dot 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 multiplied by P is equal to N1 plus N2 plus N3 plus dot 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 divided by N multiplied by P. And we just said that N is equal to N1 plus N2 plus N3. So this is N divided by N multiplied by P is equal to P. So the sum of, and this point can become confusing sometimes. So the sum of partial pressures is always equal to the full pressure. This has nothing to do with ideal gas, imperfect gas, or anything like that. It's nothing on Slack. Ideal or perfect, perfect or real, anything, doesn't matter. You know, ideal, perfect, real, irreal, complex, gas, whatever. It's always true. And my dog's about to go out on a walk, and he gets very excited. So he has his leash in his mouth, and it looks like he's about to go walk himself. I got a bit distracted, sorry. So this is true for all gases. And however, the point of, so there is no confusion so far. The confusion comes with something called Dalton's law. Dalton's law applies only to perfect gases. And what that law says, it says that if the gases were ideal, then they would be oblivious, they would be completely unaware of the existence of any other gas. Indeed, they would be even unaware of existence of each other, right? An ideal gas means I am occupying this box on my own. I don't care who else is there. Like that's the model of the ideal gas. They don't talk to each other. And as we saw, it gets approached in low density limit. So Dalton's law says that if the gases were ideal, then the partial pressure would be the same as what they would have experienced if they were in the box on their own, right? It's kind of obvious. I mean, if it was so easy to get a law named after you these days, we would all have so many laws. It's really obvious now that you think about it. So let me write it down. It says that if gases were ideal, then partial pressure is, what do I mean by partial pressure? That thing Pj is equal to xj times P is the same as the pressure the gas would exert if it was in the container all alone. So that's Dalton's law. It is valid only for perfect gases. Most things are not perfect. So those of you who are going to do PChem in practice, it could be in your chemistry, it could be in your biochemistry, geology, material science, whatever, you will find that in general, this is not true. And that leads to a variety of, I would call it fudge factors. They often go by the name of things such as fugacity and activity coefficients and things like that that account for the deviation from this ideal-like behavior. So that's all I wanted to mention about Dalton's law. It's really a trivial law. It gets confusing sometimes. What we have said so far is that we can define a partial pressure given by mole fraction multiplied by the total pressure. This is true for everything, perfect or real. And however, this will also be the pressure of the gas if it was in the container on its own, in case it was an ideal gas. So there's nothing profound here. Now we get to the more fun part. Now we are going to talk about the kinetic model. What we are going to do is to look at the gas molecules moving around and really look at their look at them from a physics perspective and try to derive connections between pressure and velocity, temperature and velocity. So the net output of this exercise that we are going to do at this point is that we will get, what we are going to show here is that there is something called a root mean squared velocity that is given by 3 multiplied by gas constant multiplied by temperature divided by m to the power half. This is what we are going to derive. And I want to give you a bit of intuition into what is it that we are going to derive. Sometimes derivations can be very dry because you kind of get lost into what is it that you're trying to derive. In fact, when I was very young, well, your age, I had this dream of trying to be a mathematician. So I went to an elite math school in India. And in my second or third lecture, we had a real analysis class. So let's imagine this is the blackboard, and this super nerdy professor, mathematician, comes to the blackboard and he writes THM, theorem. And he scratches his head and he goes like, I don't remember the theorem, but I kind of remember the proof. So he goes a little below, writes proof, and then he continues to write all sorts of math for the next 2 hours. And then he goes, now I remember the theorem. I realized I don't want to be a mathematician at that point. So I left. That killed my dream of being a mathematician. It was a sad experience. So what we are trying to do here is to look at the velocities of the gas molecule. So anytime you have a bunch of gas molecules in a box, what is the speed which they are moving? Are they all going to move with the same speed? Never, right? It's simply not possible that they can move with the same speed. You're going to have a fluctuation in the speed of the gas molecules. So typically, so let's try to think about the range of speeds that these gas molecules are going to take. So let's say we have a velocity v, and this actually could be positive or negative. So my 0 is over here. I expect, yeah, this corresponds to some negative value, but it's just a qualitative graph. And we are talking about the probability of observing a gas molecule with a certain velocity v. How is this going to look at? At 0 temperature, we expect it to look like this, right? Nothing moves. At 0 temperature, it's the only temperature at which all velocities are the same. They are 0. At 0 temperature, P of V is going to look as what is called a delta function of 0, right? Nothing moves. As you increase the temperature, so I keep calling it, yeah, yeah, if it was speed, then I could have kept the 0 on the axis, but it is velocity, so let's stick with that. So as you increase the temperature, this thing will broaden. As you increase the temperature slightly, it will start to look like this, right? As you make the temperature even larger, it will start to broaden more and more. So if you have a bunch of gas molecules just moving around, on an average, you can notice two things here. Irrespective of the temperature, what is the average value of V? Any guesses? Write on Slack or Zoom. You got some answers? 0, precisely. You see, it's symmetric, right? It's always going both sides of 0. So the average is always 0. But how about the average value of V square? That's not going to be 0, right? Average value of V square is not going to be 0. And the average value of V square is what we call the root mean squared velocity. And that's what we are trying to calculate. And we will show that this root mean squared velocity is closely related to the temperature of the system. It's closely related to the pressure of the system. And in fact, this is the expression that we are going to derive today. It's quite nice. So is the y-axis pressure as a function? No, it's not. It's not pressure as a function of velocity. It's capital P. So it's probability of observing the system with a certain velocity. Okay. So let's go back to thinking about our VRMF and how it connects to temperature. So for this, we are going to work. So this was our output. That's what we are trying to show here, and let's work through it. So the derivation is going to look something like. No, you're not mixing it up. It's confusing when you have small p's and big p's and you have a dinosaur of a handwriting. But actually, it's not that bad. I should be nice with myself. So let's think of an ideal gas. We had 3 ideal gas conditions, right? So we will start by assuming ideal gas. So we looked at a bunch of ideal gas conditions last time. The first one was that the gas is made up of molecules of mass m, which are always moving. They never stop moving. They observe classical mechanics. We are not talking about quantum mechanics. They observe Newton's law of motion. They are always moving. When temperature is 0, are the pressure and velocity always the same? Well, we will derive the expression. You look at it. You see for yourself. Thanks, Kitty. It's a good question. So let us do the derivation and then we will look at that. It's a good question. Let's see what turns out. I don't know the answer myself. Let's see what expressions do we get. It might be right. So the molecules of mass m, which are always moving per classical mechanics. Second key assumption, what's the page number? The second key assumption is that their size r is much smaller than the average separation. And the third key assumption is that the collisions with the wall, remember they don't collide with each other because the density is so small, right? So if they collided with each other, things would change. And that leads to the virial equation of state and things like that, which we'll look at later. So, so collisions are brief and elastic. What does that mean? The kinetic energy before the collision of and after the collision are the same. So for these three simple assumptions, we will derive the relation between pressure and temperature, velocity and temperature. So first let's look at pressure in a very systematic manner. So let's draw our box again. We have a box, and let's join the walls. And so what we are interested in is this wall. Let's focus on this wall. We could have focused on some other wall also, but let's focus on this one. This wall has an area A. And we are going to look at a particle, a gas molecule over here that was moving towards this wall. It comes to this wall, it hits it. It's an elastic collision. So as it hits it, it's going to go back something like this, right? That's what we are going to look at. And let's say that this is our x-axis. This is our y-axis. So as per screw rule, the z-axis should be going up, right? So I guess that's our z-axis, but we are not really talking about that. Did I get it right? Yeah, I got it. So we are looking at the x-axis. So let's say that the velocity of this thing was v. So the component of the velocity along x-axis is vx, okay? So we want to characterize the pressure. We want to write it down mathematically. Where does pressure come from? It comes from impact on the wall. So any molecule of mass m that is colliding with the wall contributes to the pressure on it through rate of change, through change in momentum. So what we need to do here is to talk about change in momentum. That's why the P symbols get even more confusing, but I will write down explicitly delta P. Okay, this is momentum, is equal to, so note that this wall is oriented perpendicular to the x-axis. So when it collides with it and goes back, the momentum is going to change only in the x direction. It's not going to change in the y direction. It's not going to change in the z direction. So this change of momentum will be given by, it was moving with plus mvx, and now when it starts to come back, it will be minus vx. Why? Because there is law of conservation of momentum, right? It's a direct consequence of Newton's law of motion, that the linear momentum must be conserved, and momentum is a vector. So if momentum is conserved, it's going to be conserved for x separately, for y separately, for z separately. So we are here using the law of conservation of momentum in the x direction. So this will be given by plus mvx minus mvx is equal to plus 2mvx. And why are we not worrying about the change in momentum in the y direction? Because notice that this wall is wall of area A perpendicular to x-axis. That's why we don't care about y or z. There is no change in momentum. There is nothing happens there. It did not, that stuff is conserved. So that's our change in momentum. So, and notice that we are interested in the rate of change of momentum as per Newton's law. So what we want is the total change in momentum. This is due to one gas molecule, right? So far, so what we need is the total change in momentum. We will have to think about how many gas molecules do we have in time delta t, which is some small amount of time. So what is this going to be? This is going to be delta p, the thing that we wrote over here, multiplied by number. My hash is supposed to indicate number of molecules that reach the wall in time delta t. This is kind of a subtle concept, but it's not too hard if you think about it. So we are thinking about a small amount of time. And if one molecule that hits the wall undergoes a change of momentum of plus 2m Vx, then the total change in momentum in the time delta t is going to be delta p, this plus 2m Vx, multiplied by the number of molecules that actually do undergo a collision, right? And there is no difference between them. Another subtle fact here is that we are not yet talking about the probability distribution of V. We are just saying there is some Vx. We are not talking about how does the Vx actually vary, because in the last slide, I just told you about a probability distribution, but we are not talking about that over here. So we need to figure out this thing. What is the number of molecules that reach the wall in time delta t? Let's say this thing that we are going to try to figure out is n prime, right? Total, we had the total number of molecules in this thing was some n, but not all of them are going to be reaching the wall in time delta t, right? If you make delta t smaller, n prime will become even smaller. If you make delta t tends to 0, n prime will tend to 0. Thomas says the change in momentum is minus 2 mvx. It doesn't matter. It depends on whether we are talking about before minus after or after minus before, right? In this case, I'm talking about before minus after. So I've defined it explicitly that it is change in momentum before minus after. If you were talking about after minus before, then yes, it would be minus 2 mvx. So let's keep that in mind that we have defined it before minus after. When we go to first law of thermodynamics, these type of sign questions becomes even more important. And in fact, the difference between whether you get a B or a B plus in this class, or half a grade difference, might depend on how you treat your signs for first law of thermodynamics, if you're careful or not. So the signs are important. So thanks for raising that question. For now, let's just be consistent with what we wrote. So we have to figure out n prime. How do we do that? So let's go back to our box. And I can't wait for my bigger iPad to get here on Sunday. Then I won't have to flip screen so much. It's a bit annoying. Because when we teach this class in one of those classrooms in chemistry, there are 8 blackboards, so that life is so much simpler. I don't want to draw the whole box. I just want to draw, remember this area, the red shaded area, I'm just going to focus on that one. So keep this red shaded area in mind. Keep this in your heads. And let's draw that over here. So we had that wall over here, right? The red shaded area. And now we are going to think of a certain thickness next to this.
The screen is frozen.
Oh yeah, sorry about that. But that's so sad because I drew such a nice smiley on that one. I will have to show you again. So it's interesting. The other day I was ranting about Zoom and how you should short that stock. It did fall by 10% that very day, but don't take my advice. Or you guys will come and sue me when you lose your money. Yeah, I drew this smiley. I was saying that keep this wall in your brain. So it's supposed to be your brain. So let's focus on that wall, and we drew it over here. And we are going to look at a certain thickness next to this wall. So this wall has an area A. And then the idea in calculating n prime is to focus on a thickness close to the wall. So the whole box is much bigger, right? It goes this way. We are going to focus on a length, given by Vx, whatever the speed was in x direction, multiplied by delta t. So the idea here is that all particles inside this volume given by area multiplied by Vx delta t will hit the wall at some point in delta t, right? So if you have a particle in this region and you wait for a time delta t, it will hit the wall. It might hit it sooner, it might hit it later. If you had a particle over here outside and it was traveling with a speed Vx, then in time delta t, it has to travel a distance Vx delta t. It has to travel a distance more than Vx delta t, right? So it won't be able to hit the wall. That's the simple idea. So as per this argument, n prime should be equal to capital N, which is the total number of molecules, multiplied by this volume, A Vx delta T, divided by the total volume of the box, right? So this is the fraction. This is the fraction of molecules in that tiny box by the wall. Is this correct though? Is this really n prime, or did I screw up something? Any ideas? Half. Elizabeth says it half. Elizabeth, do you have audio? Can you explain to us why half?
I'm not really sure why, but I think it's just because you have to assume that half of them are going the opposite direction.
Yeah, so you have no reason not to be not sure. You said exactly the right thing. When I say that this one over here, thanks Elizabeth, this one over here will hit the wall in time delta t, that's assuming that it is travel in the right direction. But imagine a gas molecule over here, and I say that, oh, this has to travel only distance Vx delta t. It will definitely hit the wall. But what if it was traveling off in this direction? Then it won't, right? And since we don't know anything about the system, we can say that half of them will be traveling in the right direction. That's why we have a factor of half. Okay, so it's kind of subtle, but not too bad. So we have n prime is equal to half multiplied by n multiplied by that 10. So now we can go and write down our total change in momentum. Is going to be delta p multiplied by n prime. That's what we were trying to find. Delta p we wrote down was 2mvx before minus after, multiplied by, we just wrote down over here, n avx delta t by 2v, where capital V is the volume. And now we can multiply and divide things. The 2 and the 2 cancels. Not much else cancels. So we are left with n times mass times area times Vx squared times delta T divided by volume. What is force? Force is rate of change of momentum. So force is delta P into n prime by delta T. Normally force is just delta P by delta T, but remember we are thinking here about the force due to all the gas molecules, all the n prime gas molecules, not just the delta P ones. Yeah, so Michael asked, did I say it's half because it's assumed that half the molecules go in a different direction? Yeah, that's exactly what it is. Yeah, I'm sorry about the Wi-Fi's. They do cut out once in a while, but the videos are all online. Typically, they are online an hour after the class. So if you miss out something, you can go and watch through it. I also like posting on YouTube is because you can change the speed, and it's kind of fun when you listen to video in 2x speed, you know, and you can really power through it. So, so this will be given by, so the delta T will now go away, and we will have n m a Vx squared by volume. This is our force. We are almost at pressure now, because what is pressure? Pressure is force by area. So this A has to be brought to the denominator on the left side. You divide by it, and there we will have our pressure. So pressure is force by area, or n m Vx squared by V. This is a wonderful relation. This is a beautiful relation, I think, because this shows you how something macroscopic, you have to think about, put yourself in Germany at the end of 20th century. People didn't believe that things are made up of atoms. Even earlier 20th century or so, people didn't really think. People thought things are made up of a continuum. It's ether, this and that. One of the founding fathers of a subject called statistical mechanics, which is really one of my favorite things, and I teach it in Chem 687, is called Boltzmann. You probably have heard about Boltzmann. He's like almost like Einstein, just you have Einstein's picture with his tongue hanging out, and you have Boltzmann's picture with his hair everywhere. He was doing things like this. He was trying to look at thermodynamics from a molecular perspective as to how you have different molecules moving around, talking to each other. They're what is called ensemble averages. And his ideas were so ridiculed upon that he got depressed and committed suicide. And a few years after that, Einstein came and started using those ideas and won the Nobel Prize. So this stuff is obvious to us now, but it wasn't obvious 100 years ago. And you can see what we have achieved here. We have derived a relation for the pressure from a very molecular perspective. We can really think of the pressure as how it relates to the velocity of things. So now let's keep going further. Now we have to keep into mind that what is Vx? Where does Vx come from? What is the value of Vx, right? So not all molecules travel with the same Vx at any finite temperature. If you had temperature is equal to 0, and my stupid screen froze again. So not all molecules travel with the same Vx. This is not obvious from what we have done so far. What we have done so far doesn't tell us why this should be the case. I'm just stating this fact that there is going to be a probability distribution of the speeds with which molecules travel. And we drew that probability distribution. We saw that at 0 temperature, it's going to look like a delta function. It's just going to be a sharp peak. I should have marked it down here. So broadens as temperature increases, right? That's the whole idea here. This thing broadens. So we have a distribution of velocities, and as the temperature becomes higher, the distribution broadens. So at 0 temperature, we know it's a delta function. On an average, we can say that, and we know that Vx itself is going to be 0, but Vx squared, the average of Vx squared is not going to be equal to 0. So I used a symbol here. This, for those of you in 482, you will get very familiar with this symbol. It's called the bracket notation. It comes from Dirac. In quantum mechanics, it's used quite a lot. It's a notation for average. Is the notation for root mean squared velocity just VRMS, or is it VRMS squared? It will become clear in a moment, just hold on. So we are talking about the average of the squared velocities, okay? So let's look at that. So one thing to keep in mind that on an average, this notation just means average. We could have also written it as Vx squared average. That would be the same thing, okay? But this is a bit clunky, so I like to use the bracket notation. I will be flipping back and forth between them. It's nothing profound, but when you start doing quantum mechanics, it does become profound because it depends, in quantum mechanics, it depends on what wave functions do you have and things like that. So you will have further operators showing up on both sides, and it's a lot of fun. You will enjoy it in 482. I think probably Amy will be teaching it, Amy Mullen. So on an average, Vx squared must be equal to Vy squared must be equal to Vz squared Why do I say must? Because in this problem, I did not impose anything about difference between the three directions. You might say, well, maybe gravity is acting in z direction. I didn't tell you anything like that, right? I'm just saying all three directions are symmetry. There is no difference. So on an average, Vx squared is equal to Vy squared is equal to V3 squared. So what we can say is that Vx squared, therefore, is 1/3 of Vx squared plus Vy squared plus Vz squared. Keep in mind, this is not the same as square of the average. Square of the average would be 0 because the average is 0. So if you take square of the average, that's also going to be 0, right? So there is a subtle difference here. I'm going to ask you in one of the homeworks or exam to think over it. And so make sure you remember this, that this is not the same as square of the average. That's different. So Vx squared, average of Vx squared is the same as 1/3 of the sum of all three averages. And that is what we define as VRMS square. That answers the question that was asked on Slack. So we have defined VRMS square is equal to Vx square plus Vy square plus Vz square, okay? Therefore, what do we get? PV is equal to 1/3. So what are we doing over here now? We are going to use that pressure is equal to NmVx squared divided by volume, right? We are going to use this equation that I marked with the arrow. So if I bring volume to the left side, we get pressure times volume is equal to Nm multiplied by Vx squared, which we just showed is 1/3 VRMS square. This is a form of ideal gas law that you have probably not seen before, right? It's a bit different. So if we compare it to the ideal gas law that we all know and love, ideal gas law says that PV is equal to nRT, right? So we know that PV is equal to nRT. We just derived that PV is equal to 1/3 Nm VRMS square. And just to be consistent, since I have been using capital N, I'm going to use capital N here also. So these two things must be the same. The right-hand side of this and this must be same. It's the same thing that we are looking at. And we assume the same model, the same ideal gas. So we never really derived ideal gas law. We kind of assumed it through experiments. There are ways to derive it, but we assume it as an observation for ideal gas. So once we compare these two, what do we get? We get that, so let me write it down again. On one side, we have PV is equal to nRT, and on the other side, we have PV is equal to 1/3 Nm VRMS square. What does that mean? If you compare both of them, it means that nRT must be equal to 1/3 Nm VRMS square. The n's cancel, and we are left with VRMS squared is equal to 3RT by M. And this is the relation that when we started doing this, we were trying to derive. So if VRMS squared is equal to 3RT by M, therefore VRMS is equal to square root of 3RT by M. So for those of you who are unhappy, a couple of you emailed me that you didn't like the derivation of the ideal gas law, you found it ad hoc. I hear you. It's a bunch of experiments that we just joined together. Another way to derive, you could think of this whole thing from an opposite perspective. If you had some other way of showing that VRMS is given by this thing, then you could have used this to derive the ideal gas law. Does that make sense? If you could have shown this is the case, then you could have gone and put in this in the equation for PV that we just derived and shown that, oh, wait, we get PV is equal to nRT. And that would be a derivation of the ideal gas law. And in fact, this can be done. You can actually derive Vrms is equal to this thing by not assuming ideal gas law, by assuming Boltzmann distribution and a bit of math. I think Atkins does it in 1.b.2 for an alternate perspective. Please read it. It will not be on the exams or homework, but if you're interested, you can go and read it. So we will just stick with this, that this v root mean squared velocity is equal to 3RT. This is actually a super interesting expression. Let's look at this a bit more. What does this tell us? This tells us that Vrms squared is equal to 3RT, right? Let's multiply it by half both sides. Half Vrms squared is equal to 3 by half RT, okay? Now remember that Vrms square was 3 times Vx square, or 3 times Vy square, or 3 times Z square. So half M, so this I like a lot, this what I'm doing right now. So this 3 Vx square is equal to 3 by 2 RT, or 1/2 M Vx square is equal to half RT. This is super profound. This thing is called equipartition theorem, or equipartition of energy. So you can think of this as the kinetic energy associated with the x direction per particle, right? And you are saying that irrespective of what your speed is, on an average, the energy per particle should be half RT. If you are looking at the kinetic energy coming from 3 directions per particle, it's going to be 3/2 RT. So this half RT is a fundamental unit in physical chemistry. If you are thinking of, this is for a mole of gases, right? If you're thinking of per particle of a gas, of a bunch of gas molecules. So what I'm saying here is that half RT, and wide angle the half, just RT, is a fundamental unit for energy. When you think about energy in physical chemistry and you try to think, is the energy small? Is the energy large? What does it mean? You should always think of RT. More specifically, you should think of RT divided by Avogadro's number, which is called KB, right? Boltzmann's constant, KB multiplied by T. So this KT is the most fundamental unit of fluctuations of energy in a physical system. I can give you some example for it. We have a lot of biochemistry majors here, right? So when you're thinking of a drug binding with a protein, and you're thinking of whether the drug is a weak binder or a strong binder, if the binding energy is 10 kT, it is a strong binder. If it's 20 kT, it's very strong binder. If it's kT, it's a very weak binder, because kT really reflects the thermal fluctuation in energy. So if you prepare a system at a certain temperature, you will see that the energy fluctuates per degree of freedom by kT on its own. So I gave you the example of drug binding, but you can take some another example where you think of some catalysis thing, and you have designed a material which has to stay in a certain state. And this material can transform from state A to state B. And let's say you have a barrier in the energy for going from state A to state B. And you look at this barrier and you try to count what is the height of the barrier. If the barrier is much more than kT, then A is a metastable state. You're going to get trapped there. If the barrier is much smaller than kT, only thermal fluctuations will drive you. Thermal fluctuations will be sufficient to drive you from A to B. So the equipartition theorem is basically saying that the kinetic energy per degree of freedom, or more specifically, energy because here we did ideal gas, there was no potential energy, right? So if you had kinetic potential energy, then it will still hold true. It gets a bit more interesting there, but it's the same idea. Energy per degree of freedom is half RT. That's the equipartition theorem, which comes from this kind of, well, it's not really back of the envelope. We went through it rigorously. We saw that the RMS square is equal to this much. So that's what it comes down to. So it's a good point to stop today. Let's see if there are any more questions. You guys are all helping each other out. So that's wonderful. Okay, so that brings to the end of today's class. We will be meeting Wednesday. On 9th, I will be releasing a homework through Gradescope. Some of you asked about it. Those of you who haven't used it, don't worry, it's not hard. And the first homework will be long. I deliberately did not give a homework in the first week because I wanted you all to settle in the new semester. It's a crazy time. So settle in. Next homework will be long. Get ready. Please go and brush through multivariable calculus. When we start talking about first law of thermodynamics, the next time we are going to look at this wonderful relation that du is equal to d cut q plus d cut w. And if it seems Greek to you that why does one of the d has a cut and the other d does not have a cut, you should brush up your multivariable calculus. Watch Khan Academy videos. And this is the beauty of first law of thermodynamics, that the sum of two path functions is a state function. That's where we will start our real study of this subject. Well, this is also quite real from Wednesday. So see you next time.